Okay, folks, so let's get started. So it's my pleasure to introduce Chris Glein, who's visiting us from the Southwest Research Institute just down in San Antonio. Now, Chris he did his bachelor's at the University of Washington in Seattle, where he worked in astrobiology. And then he did a PhD at Arizona State University in geochemistry, planetary geochemistry. And then he did a postdoc in Toronto and another postdoc at the Carnegie Institution for Science in Washington, DC. And he was part of the Cassini INMS team. That's the ion and neutral mass spectrometer. And you might know that's one of the teams that was publishing some of the most exciting results from the Cassini paper, mission. Chris was involved in many of those papers, including some of the discovery of things like, molecular hydrogen and the plumes of Enceladus. And he's really become a big name, one of the main people that you think of when you think of icy ocean world. So we're very lucky to have him here today, and he's going to be giving us some of the, telling us about some of the recent developments in this field. And he's also, so Cassini's over now, but he's also a person who's involved in some of these, mission concepts. And I don't want to put pressure on you, but, one of these concepts might be turning into one of the missions that actually brings us the first direct evidence of life beyond Earth. So clearly this is an exciting area, an exciting topic, and it'd be great to hear from Chris about it today. So with that, please welcome Chris Glein.
They can't shake really. It was just one person with. Oh, okay. Awesome.
We're okay? All right, so I'll get started. If there's a problem, just let me know, and feel free to interrupt me too if you have any questions or anything else comes up. So yeah, thanks, Doug, everyone, for coming. I'm really happy to be here. This is actually my first time on UT's campus. I came 5 years ago to visit UTIG, and I talked a little bit about Enceladus, but a lot's happened since then. So I'm glad to be back and to share some stories with a different group here today. So today what I'm going to try to do is we're going to take a trip out through space and time. So we're going to go out to Saturn's moon Enceladus, which is a small but mighty moon of Saturn. So I'll sort of give you some of the highlights of things we've discovered or how we're currently understanding it. And then we'll take a trip through time and really go through a whole chronicle of Cassini's and humankind's voyage of Enceladus and how we've gotten to learn about conditions and processes there. And really today, the whole angle is going to be slanted towards geochemistry, because that's what I do. And don't worry, if you're an astronomer or biologist, I'll lead you through some things and focus on the main ideas. So how this is going to work is we're going to have a few different parts to our story today. The first part is going to be all about this journey of exploration towards understanding the habitability of Enceladus. And habitability really just means, is this the type of environment that would have conditions and processes that might be able to support life as we know it? So let's just really jump into the story. I'm sorry if you're an astronomer and you already know all this stuff. For the rest of you who don't, hopefully this is interesting. So Enceladus, the story of Enceladus parallels the story of modern astronomy and the development of science after the Renaissance, where for most of human history, we knew that there were 6 planets and the sun and the moon, and we didn't really know anything else beyond that. The planets are just wanderers, right, in the night sky, which had very interesting pathways through the sky. But then we had the invention of the telescope, and we started to find that there are other bodies that we had not previously identified, particularly these moons of the giant planets. So you might have heard Galileo changed our view of the universe by discovering that Jupiter had moons that orbit it and not the Earth. So that was a real revelation. And then as you move through the next few decades, astronomers turned their telescopes to Saturn, and we discovered that Saturn also has pretty decently sized moons. So the first one discovered in the mid-1600s was Titan. It was discovered by Christian Huygens. And you hear more about the Cassini-Huygens mission. So Huygens was one of the namesakes of this fantastic mission that we developed. Then we had this guy here in the middle. His name is Giovanni Cassini. He discovered quite a few of Saturn's small moons. So shown in the middle there, Iapetus, Rhea, Tethys, and Dione. And you can see the moons. This is kind of what the moons would look like around Saturn through a pretty high-powered backyard telescope. It took until the 1700s, though, before we were able to discover the star of today's show, which is Enceladus. And the reason it took so long is we'll find out Enceladus is a very small world and it orbits close to the glow of Saturn. So you really need powerful telescopes to actually see Enceladus. I've never seen Enceladus through a telescope. I just have a 6-inch reflector telescope, and I've seen Titan, some of the other moons. I've never seen Enceladus. So, but for the next 200 years, it's great. We discovered that there's this moon that was named Enceladus, but we really didn't know much about it because it was just so far away. It's hard to really tease out any details. That all changed in the late 20th century when NASA sent the twin Voyager probes to fly by all the giant planets. So this is the grand tour when there's this unique opportunity to do flybys past all the giant planets. So we went past Jupiter, and then we did a flyby of Saturn and its moons. The first one was a Voyager 1 probe, and that one really focused on Titan. It did a close flyby of Titan before it exited the solar system. And a key proponent of doing that was Carl Sagan. You probably heard of him. He was a real major person in publicizing planetary science in the late 20th century. And Titan was particularly interesting because it's this organic-rich body that might tell us something about organic chemistry in a prebiotic environment. Flash forward a couple of years, and then we had the Voyager 2 mission, which did closer flybys of some of Saturn's other moons. So this is our closest shot, shown on the right-hand side here, of Enceladus. And immediately this captured the attention of scientists because it looked different from most of the other moons, like our moon, which are really cratered bodies. They look like they've accumulated a lot of scars throughout their history, and their surfaces haven't been too active. But on Enceladus, you can see on the left-hand side here, you see like these grooves, and it's smoother. So there was something interesting that happened on Enceladus that really captured our attention and motivated going back to Saturn with a much more capable suite of instruments. So that was in the early 1980s. I was born in 1982, so that was like a year before I was actually born is when all that excitement happened. I flash forward, and I was born. Some of you were born also after that. And then we had this other mission that was in development from like about the mid 80s all the way to the late 90s called Cassini-Huygens, after the two major discoverers of the moons of Saturn. And on the left-hand side image here, this is just showing the spacecraft with all the instruments. It's kind of like a Christmas tree, right? So we had all sorts of great scientific investigation centered around these instruments, and it was what any planetary scientist would dream of, where you'd have all different kinds of cameras looking at different wavelengths, and you'd have different fields and particles instruments. You could measure different kinds of atoms or ions and molecules that are in the space environment. Cassini finally launched in 1997, so it's kind of a tortuous path to get to the launch pad, but we finally got out towards Saturn, and it took quite a while to get there. So Saturn's about 1 billion miles away, so it takes a while to get there. You have to do an interplanetary cruise. We finally got there in 2004. This is one of the most majestic images from Cassini showing Saturn up close. If you ask me, that's my favorite planet, Saturn. All right, and so a little bit about Enceladus now. I told you it's a small but mighty moon. It really is small. So like you've probably heard of Europa, Jupiter's moon, or Titan. Like those moons are big moons, giant moons. They're kind of like roughly the size of Earth's moon. Enceladus is roughly the size of Great Britain shown here. So this is like a to scale image. Or you could plop down Arizona. Arizona would be almost around the same size. So it's really not, it's not the size of, our moon. It's really like the size of a state or a small country for comparison. So it's a much different environment from one we normally think of for interesting planetary bodies. But don't let looks deceive you. It has an interesting story to tell. We think that it's roughly about a 50-50 mixture of ice or other forms of ices and rocks. And the reason we think that is one of the most basic geophysical measurements is the density of an object. You can just you can image it and get its diameter. And then you can also make measurements of its gravity field to get the mass, or you can just calculate the density here. And the density is about 1.6 grams per cubic centimeter, which is in between water and rocks. And the last thing I'd like to point out is the gravity is about 1% of the surface gravity on Earth. So it's much feebler gravity than we are familiar with. And you'll see how this comes into play in a major way in a couple more slides. Or I guess one more slide. Okay, this was one of the biggest discoveries of the Cassini mission. I was a graduate student when this was first discovered. So around that time, that was like when the Mars rovers first landed on Mars. So there's a lot of interest in Mars and water on Mars. And then all of a sudden we found out that there's something really unexpected and exciting happening on a small moon of Saturn. And it was reported that the Cassini spacecraft detected a plume of water erupting from the south pole of Enceladus. So you can, these are just different images. Here's the plume in, like its full broad view from Cassini. And in the middle image there, you can see closer views of what are called jets. These are actually like little features on that are erupting from the surface of Enceladus. And then they eventually merge together about 20 kilometers above the surface to form this huge plume superstructure. And that's where gravity really comes into play. You can see just how far the plume goes away from Enceladus. Like this is over 1 planetary diameter into space. So it's much larger in extent than normal eruptions that we find here on Earth. And what's cool about this is this finding, it really blew away the community. And we learned that Enceladus is the smallest geologically active body in the solar system, which generally flies in the face of what we expect. So when you're taught, in an undergraduate course, bodies have more internal heat if they're bigger. And Enceladus is very small. So this created something of a puzzle for people, and we're still working out the details. You might wonder, well, where's that plume come from? And this is the modern view of where we think the plume comes from. We actually think it comes from liquid water ocean. So, we see the plume erupting from the surface, and we can see the surface. The surface is a brilliant, bright white color. It's almost like freshly fallen snow. So we know that there's a lot of ice, water ice on the surface, but we didn't know, or at the beginning of the Cassini mission, what the subsurface looked like. And now we're some of the fuzziness is starting to come into focus. And this is the picture we have, is we think that there's actually a liquid water ocean that's sandwiched between like rocky material. We call this a rocky core. And then above that is the ice shell. And then you can see Cassini there. We actually flew through the plume. And we were able to sample the plume's constituents, what's in the plume. And that was what really helped us to nail down the source of the plume, because when we flew through the plume, we had these different mass spectrometers, those in situ instruments I mentioned earlier, and they were actually able to ingest some of the plume material. So you fly through the plume and there's stuff in the plume, and we were actually then able to sample that stuff and figure out, what does it taste like to an instrument? And what we found is that the plume actually tastes salty. So this shows a mass spectrum. This is mass, and then amplitude is related to abundance of different chemical constituents here. And so you can see like the largest peak shown there comes from the sodium ion. And then, you see these other peaks that were identified corresponding to different salts containing sodium. And so we've learned through this kind of analysis that the most abundant non-water species in the plume particles is actually salt, sodium chloride, table salt, sea salt, the stuff of the sea. So that really that was a key clue for where the plume came from. It actually comes from this liquid water ocean that's in contact with rock, where the water could react with the rock and remove salts from the rock and concentrate salts in the liquid water layer. And so I have to show something from my host, right? So this is a paper from Hemingway. This has actually been superseded just recently, this work. But this is pretty close to what we think the current answer is. And we think now from all the integration of geochemical and geophysical perspectives that Enceladus, though it's small, we think it has a global ocean of liquid water, between the rock and the ice shell here. And what's also curious is from the geophysical analysis, we think that the ocean is deepest or the ice shell is thinnest right at the South Pole. And that's where the plume is erupting from. So it's kind of interesting. So, we have a lot of water on Enceladus. The ocean is thought to be about 60 kilometers roughly deep. And just for comparison, like the Earth's oceans is like 4 to 5 kilometers deep. So this is a very deep ocean, what the data are currently indicating. Now I want to move us into discussion of planetary habitability. So maybe you've seen things like this before. If you try to simplify, what are the general categories of things that life needs to support a habitable environment? Usually it's these 3 ingredients shown here, where the first is liquid water, finding water on Mars or finding water on Europa and Enceladus. That's a real driver for exploration. We think with this deep ocean that there's abundant liquid water available. So, I've added a check mark there. And now for the rest of the talk, what we're going to sort of go through is trying to understand these other 2 ingredients of habitability. One is a source of free energy, some kind of energy source that the environment provides that life could exploit to use to its advantage, to do the things that life needs to do, like make DNA molecules. And then the other ingredient is related. It's like once you have an energy source, you got to have the raw building blocks to build the machines that life uses, like DNA. So you need, carbon, hydrogen, and so forth. But let's first discuss the source of energy. Can a small moon have enough energy that life could use? And this leads to our last flyby of Enceladus. So right before the Cassini mission ended in 2015, we did what's called the E21 flyby. So that was the 21st close flyby of Enceladus by Cassini. And we detected, unexpectedly actually, mass 2 counts as we flew through the plume. So what you're seeing on this plot here, the horizontal axis shows seconds from closest approach. So you can imagine the spacecraft is flying at over 5 kilometers per second in speed, and it's zipping past the South Pole of Enceladus and cutting through the plume at about 50 kilometers altitude. So when you're 0 seconds from closest approach, that means you're like right over the South Pole. And what you can see here, this all happens very quickly, right? So, like there's no signal when you're 15 seconds away. And then once you get, like within 5 seconds of the South Pole, then all of a sudden you're seeing something interesting and then you're going away again and it's gone. But what we found within this 10-second interval was gold, right? We actually found mass 2 species using our neutral gas mass spectrometer. And the most plausible mass 2 species in that kind of environment is actually H2. It has a mass of 2. It's a hydrogen molecule. And you can see right when we passed over at 0 seconds closest approach, that's when we detected the most number of counts of H2. So it was the most H2 present. And then, it went away as we went away from the plume. From analysis of the data, we found that there's about 1% H2 by volume in the plume. Is that important? Well, it depends. If you're an astronomer, maybe this doesn't seem that shocking, right? Because if you look around the universe, hydrogen nuclei are very abundant. It's actually the most abundant element in the universe, right? So maybe it's not shocking to find hydrogen in outer space. If we go to the sun, there's a lot of hydrogen. If you go to Jupiter, this is from the Juno mission, an image of Jupiter. Jupiter is loaded with hydrogen. So hydrogen in and of itself is not surprising. But what was important is Enceladus, it's not a gas giant planet, right? Small moon. On smaller solid bodies, so now I'm giving the Earth as an example, we don't find much H2 in those kinds of environments. And the reason for that is that H2 has such a small mass, it's hard for a small planetary body to hold on to H2, right? You know, just it's hard to have enough gravity to hold on to H2. You need to be big like Jupiter or Saturn. Bodies like the Earth, when we explore, we find that there are certain environments that have abundant H2. And usually that's associated with hydrothermal processes, you know, like where the water meets the rock at the bottom of the ocean, you could have water rock reactions in geochemistry, and that kind of process can make quite a bit of H2. So we thought, well, maybe this makes sense because we know from earlier Cassini data, there's an ocean on Enceladus. We think it's in contact with rock, and now we're seeing all this H2. So this is the picture that we put forth from looking at the Cassini data is this. And, you know, this is an artist rendition. We don't actually see this, but we think that this makes sense in terms of the data we have from Cassini. And so what we're detecting is stuff in the plume, right? You know, at the surface. And what's kind of remarkable from thinking about those data is you can use chemistry as a window into the subsurface, right? So we're not able to directly send a submarine or anything yet into the ocean of Enceladus, but we're starting to get some clues of what's happening down there in the depths, which is, I think, pretty interesting. You know, we think that finding H2 is a signature of the water reacting with rock, because that kind of process, from what we know from the Earth and from lab experiments, you tend to make hydrogen when you cook up water plus rocks. And this leads to all sorts of interesting questions. You could actually go quite far down the rabbit hole. But what else? The basic question is, on Earth, when you go to these kinds of environments, there's all this really interesting geochemistry and geophysics, you know, the churning of rock and water circulating through it and high temperatures being reached. One of the dramatic consequences of that process is when scientists first discovered hydrothermal systems on the bottom of Earth's oceans, it wasn't the geochemistry that jumped out. It was actually finding life in the dark, right? So they found that there are whole ecosystems surviving in the dark, and they're actually feeding off the chemicals that come from the Earth. So now that we're finding these chemicals coming from Enceladus, there's this question, you know, could you have some kind of similar ecosystem that might feed off of those chemicals? And so what we decided to do is we decided to take our geochemical data, you know, compositional data from Cassini, and then we performed an analysis. So we wanted to answer, you know, could there be enough energy to support life? You know, this is the key ingredient for habitability. And so I'm going to quickly walk you through this chart here. The reaction that we considered is known as methanogenesis. And you can see why hydrogen is so important, because it's one of the two reactants for to make methane, right? You need to react CO2 plus hydrogen. And then what we're going to walk through here is we're going to try to quantify how much energy would be available. And we do this by this variable called the chemical affinity. It's how much free energy can this reaction provide. And, you know, there's like two parts to it. So one part is just based off standard Gibbs energies. This, you know, if you go through like any kind of textbook, you'll find in an appendix, it'll be tables of Gibbs energies. So you could find this really easily or calculate it. What's really hard, if you're thinking about other planets, is the second term here. And this is known as the activity product, or some people call this a reaction quotient. And what that term depends on is the actual measurements of the reaction species shown above there. So to evaluate delta G, the Gibbs energy, you need both parts. You can't cheat and just evaluate the first part. And that's why you actually need to send multi-billion-dollar missions out into space, is so you can gain insights into the second term. The last thing I want to show, you know, equilibrium is where you have zero energy. So that's a key point of reference to understand if the environment has enough energy for life. Here's what we think life needs from studies on the Earth. You need roughly about 10 to 20 kilojoules of energy to support, you know, the the most feeble microbes that are kind of like in a starvation state. They're almost they're almost dead. They're like half dead, but they're barely able to survive deep in the sediments on Earth's seafloor. And so the question is, that's the energy demand part of the equation. What's the supply part of the equation? And so from earlier Cassini data, we were able to constrain things like the pH or other properties of the ocean, so we could make curves like this. But the real problem with those curves like this is we had no constraints on the H2 variable. So you can see, if you go all the way to the left-hand side or even past this plot, you could go near zero energy, and that'd be a dead system. But what was really handy is once we made that measurement with Cassini, then we were able to put a solid constraint on how much hydrogen is available in an environment. If we do that, then we're actually in business then, right? Because then it's pretty straightforward to find out, well, what's the set of conditions that satisfy all the measurements? And that's shown here. That's this turquoise box shown there. And that's where we think Enceladus's ocean lies in terms of how much energy would be available for microbes. And what's interesting about that is it kind of looks like it would be, you're a microbe, you're a bacterium, right? It'd be like a feast because, this is where you're starving, right? This is like you're having a few crumbs of bread every couple of weeks, right? And then if you're way up there, 100 kilojoules of energy, that'd be quite something if you're a microbe. And so the conclusion from that exercise, combining both geochemistry and spacecraft data, was that the energy supply exceeds the demand. So we concluded that Enceladus is energetically habitable. It has enough energy for life. And so that brings us back to this plot shown here, where we think there's a source of free energy that life could use. And let's discuss the last part here now, essential elements. Unfortunately, I can't give like a 2-hour talk, so we have to skip some of those elements. They're important. So we'll skip these ones. We found evidence of carbon, nitrogen, and so forth, and some weak evidence for sulfur. The one that was a real kicker, though, was phosphorus. And phosphorus is usually the rarest of the major requirements of life. That's why, so we're in Texas, right? So if we dump fertilizer into the Gulf of Mexico, it's a bad thing because microbes will go crazy, right, in the Gulf, because they're often phosphorus limited. So it's a really key ingredient for supporting the growth of organisms. And, here, I guess I'm summarizing this again, right? So, phosphorus is a major building block of life. Our DNA molecules are the connecting pieces of DNA are phosphate linkages, they're called. The key molecule that allows, me to swing my arm like crazy up here is ATP. So it's a way of converting different forms of energy within the cell. And without these phosphate linkages, we don't know how life would be able to convert different forms of chemical energy. I already mentioned the Gulf of Mexico. It's often a key, phosphorus is a key limiter of microbial growth. So it was a real question, is there enough phosphorus? We think it's important. We're interested in Enceladus as a potentially habitable environment. We didn't have any data, at least in, the beginning of 2020, when I first started thinking about this. This is like right before the pandemic. I met with my friend at HEU, and we decided to try to work on this problem. We originally looked at some data from carbonaceous chondrites. We think those might be the building blocks of icy moons. And we found that phosphorus, it's not as abundant as silicon or magnesium, but it's not extremely trace either. There's a decent amount of phosphorus available. So we think, on a whole planetary scale, we think that phosphorus would be present. But there's this key uncertainty. We didn't really know, what form phosphorus would take on an icy moon, or how much would be in the ocean. So let me walk you through some of the things that we started to do to try to understand this. This is a diagram aqueous geochemists like to make to try to understand, some general aspects of how a system behaves. So I'm plotting, you know, the vertical axis, that's the activity of hydrogen. So that's basically how reducing the environment is. And pH is something that quantifies how acidic that environment is. So how acidic Enceladus's ocean is. And what we did is we just made this plot and we looked at it. And you know, you have different phosphorus species shown here. And what was interesting, we made this plot, is we used Cassini data to constrain, you know, where Enceladus might be on this plot. We think it's someplace down here. And when you look at the stability fields of different phosphorus species, the only ones that really matter in this kind of environment are the phosphate species, you know, H2PO4 minus or HPO4 minus 2. So phosphate is a kind of phosphorus that life on Earth uses. Ooh. I think I said everything already. Okay, so let's move on. So the question then is, you know, how much we think phosphate is probably what's going to be the game in town for Enceladus. How much phosphate might be in that ocean? And so we decided to do some geochemical modeling. This is building up an approach that I published in 2020. And it's a really simple approach to try to get started. You know, it's the idea to take all the compositional constraints we have from Cassini. It helps us understand, you know, like how much sodium is in the ocean, how much ammonium or how much hydrogen. Putting those constraints into the model. And then for things that we didn't really know, like, you know, how soluble calcium is or magnesium, we assume that mineral solubilities would control those elements. And so, you know, it's a combination of both observations and some simple theory. And if we do that, we can then make predictions, you know, what kind of minerals would be stable in contact with Enceladus ocean water. And that's shown in this diagram here. And then you can see, I'm just going to focus on phosphorus. So, you know, different types of phosphate minerals are predicted to be stable at different pH conditions. And so one of the diagrams here shows without fluorine, the other one is with fluorine. And the reason we made two diagrams is we don't actually know how much fluoride is in the ocean of Enceladus. So we just kind of try to pick both cases. And the reason fluorine's important is fluorapatite is a pretty stable mineral, so you have to consider it. Anyways, if you do that, then you can predict how soluble those phosphorus minerals are under Enceladus ocean conditions. And that's what we did. So this shows our result here as a function of pH for those two different cases. And then, you know, we consider a lot of different end members spanning the data from Cassini because there's still uncertainties in a lot of properties of the ocean. So that's why you don't see any kind of single prediction. You see this band of possibilities that's shaded in gray. But what was most interesting to me when I looked at this band, we first produced this plan, I think it was like early 2020. So this is like right when the pandemic started and we were at home talking about this on Zoom, is we compared that to modern Earth seawater. You know, modern Earth seawater has about 1 micromolar dissolved phosphorus. And for almost all the cases for Enceladus, we found that the predicted phosphorus solubility should be very similar or much higher than what we find in modern Earth seawater. So that was kind of unexpected because normally you think, well, phosphorus is insoluble. So that's kind of surprising. But that might support habitability on Enceladus. So we thought that was interesting. And I was working with somebody else. I've been working with him for quite a while. His name is Frank Postberg. He's a professor over in Germany. And he's one of the key people who analyzed Cassini data from what's known as the dust mass spectrometer. So it's looking at different solid particles in the plume. And I told him about these predictions. He thought that was interesting. And then he's been looking at the data for a long time, years. He's spent looking at the data. So he decided to take another look. And what they chose to look at for this investigation was the E-ring of Saturn. So, you know, Saturn has these different rings. The really bright ring is known as the B ring. The E ring is the ghostly ring shown here. You know, it's just like this halo around Saturn. And what's interesting about the E ring is it's coincident with the orbit of Enceladus. And we now know that the reason Saturn has an E ring is because Enceladus, its geysers are shooting out these particles, and some of those particles actually go into orbit around Saturn, and then they get trapped in the E ring. So you could sample the E ring, and in a sense, by sampling the E ring, you're actually sampling the ocean of Enceladus, because the ultimate source of those particles is the ocean. And what they found, it was pretty shocking actually. What they found is they found a population of sodium phosphate rich grains. So I just put this box around those peaks that correspond to phosphate species. You know, you can see the chemical formula that are listed here, and 3 really strong signatures of different phosphorus species. So we thought that was really interesting. And what this discovery means is this is the first detection of phosphorus coming from a liquid water environment anywhere, actually, not even Mars. I mean, Mars, we talk about ancient liquid water for the most part, but here we have extant ocean, you know, present day ocean, where we think phosphorus is present in that environment. We weren't totally convinced yet. So then over like the next year or so, Frank's group did a lot, and some other workers in Japan did experiments to try to really convince ourselves that this is real. And what we found is when you do a lab experiment, it's a pretty simple lab experiment actually. So what you do is you just make solutions of sodium phosphate salts. You subject it to similar conditions at which Cassini detects these salts in the plume. So, you know, that's like a high-speed flyby, right? High energy conditions. And then you collect mass spectra. And what they found, you know, it looks a little different, right? Because this is actually a modern mass spectrometer. It's not one from 30 years ago. But you see the same 3 peaks as what Cassini found coming from the plume. The same 3 sodium phosphate peaks are produced. And they're really what we would expect to have if you have phosphate salts dissolved in water. What they found is, and then you can vary your experiment, right? So you can change the phosphorus concentration, and you can try to have a best fit to the data. And when they do that, the best fit is roughly around 1 to 10 millimolar in concentration. And what I told you earlier is on Earth's ocean, it's usually like 1 micromolar. So we're talking about a liquid water reservoir that has 1,000 times higher concentration of phosphorus than Earth, average Earth seawater, which is really remarkable if you think about it. And it shows, even earlier we predicted that Enceladus might have a phosphorus-rich ocean, but models can be wrong. But even if you don't believe that model, this is a real measurement of data from this extraterrestrial environment, and it shows that phosphorus is abundant in the ocean of Enceladus. A little bit of geochemistry, in case you haven't had enough yet. This is a reason to learn general chemistry. So it's really a beautiful illustration of how general chemistry works. And the way you can think about why phosphorus is abundant is just considering 2 coupled equilibria. So one involves carbonate mineral dissolution. So calcium carbonate, calcite, dissolving. And what you find is that on Enceladus, we think the ocean is rich in soda. Carbonates, bicarbonate, and those kinds of species, we have data showing that. And in those kinds of environments that are rich in soda, that means the concentration of dissolved carbonate species is high. Let's move this thing here. If you have abundant carbonates on the right-hand side of the equation by Le Chatelier's principle to maintain equilibrium, that means other stuff on the right-hand side has to be lower to balance out the effect. So it tends, in a carbonate-rich system, you tend to have low calcium concentrations in the water. Now, if you move down to the next equilibrium, where you have phosphate minerals dissolving, like apatites. It turns out that, that there's different species involved. Calcium is really critical. It has a stoichiometric coefficient of 5. So that means it has a big effect. If calcium is low from that previous equilibrium, that means the other stuff on the right-hand side of the equation needs to now move up to compensate, right? So you have this drive, thermic drive, and to make phosphorus shoot way up than you normally are familiar with. And it's really because you have a soda ocean on Enceladus. It's a little different from Earth seawater, where we don't have a soda ocean. And this just shows it in pictorial form here. The same things I just described. You have this interplay between carbonates and phosphates and dissolved carbonate species and dissolved calcium and dissolved phosphorus, how they interplay with one another through very simple equilibrium chemistry. And that naturally predicts high phosphate concentrations. We tested this. So this is in the paper before the discovery. We tested this. So, you can use an equilibrium model and you can just vary the concentration of carbonates that are in the ocean. And if you do that, you produce these beautiful linear correlations. You see the ocean gets more soda rich, the concentration of phosphorus is predicted to shoot up to very high values. If you don't like models, because some people don't, you can go in the field and you can find they're called soda lakes. Who would have thought you could find Enceladus here on Earth? But there are actually some environments, these soda lakes, that are found. They're really common in the Western US, where you have like arid environments where water's evaporating. And in these soda lakes, you find that when you have high dissolved carbon concentrations, over here, there's this correlation with phosphate, where phosphorus becomes very soluble and abundant in the water. And, there's the Enceladus data shown here. So it actually fits in really well with this soda lake type model that ultimately boils down to equilibrium geochemistry. Okay, so here's today's view of Enceladus habitability. It's pretty well understood now. I'd say if you have a keen eye, this check mark is a little smaller because we're still not totally sure about sulfur. That's a species that remains a source of uncertainty. There are some hints that H2S might be present in the plume, but they're kind of weak hints. So I'd say the case is strong, but it's not a complete case yet for habitability. Okay, so we're almost done. We got like 5 minutes, and I got this whole other part of the talk to tell you about. Luckily, part 2 is yet to be written, The Search for Life. I will tell you a little bit about what we're going to do, what we are planning to do. So this is 2 years ago. The National Academy of Sciences, they commissioned a study known as the Decadal Survey, where they solicited the scientific community to provide their reasons to go to different places in the solar system and why we want to go to places to answer big questions. And it turns out Enceladus was prioritized. You can see at the bottom of this list for this decade is to start a major new mission to Enceladus that's called Enceladus Orbilander. So this is big. This is the first time the National Academies has explicitly recommended to NASA that you should develop a mission to go search for life on an icy moon. What is Enceladus Orbilander? Its name is Orbilander. So it's going to do 2 things. One is it's going to first orbit Enceladus. And it's going to do that for quite a while here. And what it's going to do is 2 things in orbit. It's first going to complete our habitability assessment by analyzing the plume. We'll look for the sulfur, the missing sulfur. We'll also look for organic molecules that we haven't found yet. And the most important thing we're going to do is we're going to find a safe place to land, because you got to perform detailed recon, right, before you want to land on the surface. So we'll do that. Once we've found a safe place to land, then the mission gets really exciting, because they're going to land this thing on the surface of Enceladus, hopefully someplace close to the South Pole where the plume is erupting. And then we're going to have a set of instruments. These are like, analytical chemistry instruments that will have things like chromatographs or mass spectrometers, state-of-the-art systems that are meant to look for signatures that scientists have decided are the best ones to look for evidence of life on Enceladus. And we'll be taking this spacecraft, and we're actually going to be scooping some of the surface, because the surface is kind of like freshly fallen snow. And we'll be scooping up that surface, and the spacecraft will be doing chemical analysis to look for molecules that might be signs of life. The problem, this is a big problem actually, is this mission may not get there until 2050, which is great if somebody's an undergraduate or if they're on Zoom right now. This might be your mission, or if you're a grad student even. I'm not sure if it'll be my mission, because I'm not that good. But what can we do between 2024 and 2050? Because this is a really interesting system, and it would be a shame if we got to just sit in hibernation for the next 25 years. There's something we can actually do. NASA developed this major telescope over the past couple decades called the James Webb Space Telescope. It's now parked in orbit around the sun, and it's operating beautifully. And it's pointing at all sorts of interesting places in the solar system and outside the solar system. And it turns out we pointed it at Enceladus. It looked at Enceladus late in 2022, and we published our first data in a paper last year. So this just shows some of the highlights from that paper. Showed up here, this is the infrared spectrum of Enceladus. So far, we haven't really found anything too shocking in the surface spectrum. So the surface looks like bright water ice, like we would have expected. What was really cool, though, and was unexpected, is we actually detected embedded on the surface spectrum, we saw small features within that surface spectrum. If you zoom way in, you can actually see, maybe you can see little blips shown there. If you zoom in here, you can actually see these blips closer up, and you fit those to a model. They coincide really well with fluorescence light emissions from water molecules. So what happens is, the sun is shining on the plume, and it will actually photochemically excite water molecules, which then fluoresce. And we can detect those fluorescent signatures using James Webb. So the bottom line is JWST can see the plume. And we did not expect this. This is a small moon. It's erupting this plume, but it's still small. It's really far away. It's 1 billion miles away. And we were actually able to then use this telescope, which is fairly close to the Earth still. It's not in Earth orbit, it's close to Earth. And we could resolve and detect the plume. And just to give you a sense, what was shocking to us is this pixel here. That's Enceladus. It's 1 pixel to James Webb. But beyond seeing that 1 pixel, we were able to resolve and see structure and detect the plume, stretching out not just, a couple Enceladus radii, like we saw from Cassini, but now we can take a big wide field view of the plume, and we can see that it extends around 10,000 kilometers into space. So it's a huge structure that's erupting from Enceladus. And it has a lot of effects all throughout the Saturn system because, it makes the E-ring, right? And it also pollutes a lot of the other moons of Saturn. So Enceladus is, although it's small, it's very influential. It has a big voice, right? So what we also found, we did more detailed analysis. It actually looks remarkably similar in its eruption properties to what we found from Cassini. So it looks like it's a cold faithful, like Old Faithful, it's cold faithful, right? It's been trucking along, and it seems remarkably consistent over around a 20-year time frame, at least, since we've been observing it with Cassini and now James Webb. And the fun is not over yet. So we wrote a proposal last year, and this was actually selected for observations. So I'm the PI of this proposal, and we're scheduled to observe in June of this year. And so the last observing proposal, in case you quickly noticed, we observed for about 5 minutes. And in this program, we got about 50 minutes of science observing time with James Webb. And we also have optimized some other properties with the detector and other things. So we're expecting around a signal to noise boost of around a factor of 10 with these new observations. So we're hopeful that we'll be able to see some new things on the surface of Enceladus. We might detect some new species in the plume. We'll be able to test some of the things that Cassini taught us, or what we currently think is happening at Enceladus. And we're really excited about this. So stay tuned for hopefully some exciting results later this year. And with that, I think we're out of time, and you can read through these slides and ask questions. Thanks. Thank you.
Time for a couple questions, I think.
Yeah, sure. Yeah, that's my place. You're right.
Oh, there isn't? Okay, great.
Not this year.
Oh, that's even better. So, a few questions.
I have a question. So why do we think Enceladus had, what causes the soda ocean? Why is the Earth ocean not soda ocean, and why is?
Yeah, it's a good question. I looked at this 4 years ago now, right before the pandemic. We think that Enceladus formed out of icy building blocks that might resemble comets. And comets have abundant CO2. So it looks like Enceladus just started with a huge CO2 inventory. And I think that's probably the main factor to make soda. Soda is just a neutralized form of CO2.
We also like predicting I think nobody can actually from basic geochemistry predict the Earth ocean composition, right?
People
It's
have.
remarkably hard thing.
It's hard. I mean, people have ocean models. Earth's ocean may be much more complicated than Enceladus because on Earth you have sunlight, right? And you have continents. So you have like these different subsystems in the Earth system that makes it more complicated. On Enceladus, I'll knock on wood, maybe it's simpler because we think you just have, an ocean, ice shell above that, and seafloor, and you don't have all these highly disequilibrating processes like you have on the Earth. Yeah, because people, on Earth, you have continental weathering, you have seafloor weathering, you have hydrothermal systems, you have life. We don't know if life is affecting Enceladus yet. Yeah, anyone?
Okay,
We're gonna talk.
thank you for the talk, it was really cool. I was wondering about I guess, in what form do you most expect to see sulfur? If you were to detect sulfur, what's the most likely one, or most expected?
The most likely form would probably be iron sulfide, like pyrrhotite. We may not find that because it's pretty insoluble. So we could find trace levels of H2S, which would be derived from pyrrhotite. The most exciting form of sulfur to detect would be sulfate, because it would be in a state of disequilibrium with H2 and methane. So that would be another potential source of metabolic energy in addition to methanogenesis. Yeah.
Okay, so, cool. Did you detect phosphorus either on the surface or spectroscopically in the E ring other than with CDA?
No, we have not.
Could you
I'd have to look.
phosphorus in some form fluoresce?
I'd have to look. Maybe there are some bands in the near infrared where you could detect phosphate. That'd be really great since we're going to use James Webb in the next few months. That would probably be the best bet to detect phosphorus, I think, remotely.
Because the CDA bands were pretty wide.
CDA's bands are wide. The reason for that is the instrument is a low resolution mass spectrometer.
But you had more than one bin in a spike.
Yeah. Yeah, I think I would be surprised if we can do it remote sensing. Probably what we'd want to do is send, Orbilander or some other mission to Enceladus with some kind of wet chemistry experiment that's more directly measuring phosphate. It'd also be very interesting to look for organophosphates actually too, because that's a little bit different from sodium phosphates.
If not, there are hydrogen systems. Are there any other hypotheses for how hydrogen gas could be produced on Enceladus?
Yeah, well, there's another process that can make H2 called radiolysis. There's two ways that can happen. One is you can have charged particles. So Saturn, the space radiation environment, it's not like Jupiter, but it's still pretty wicked. Like you wouldn't want to stand there, for example. So there is some of the water ice on the surface that is decomposed via electrons and other sources of plasma, and that can produce some H2. That's one source. Another source of radiolysis can be in the interior, where radioactive elements, when they decompose, you can have gamma or beta emission, and that can help slice and dice water molecules to make H2 also. We try to quantify those processes, and they don't seem to be large enough to make enough H2 to explain the data. But those are two additional sources of H2. Yeah.
Kind of was similar to actually the question I was gonna ask about whether there's any kind of like dissociation of water in the plume itself, not on the surface, prior to measurement. That, like, given the H2O ratio, is that ratio too large to be explained by chemical dissociation?
So we haven't calculated that process yet. That's a good suggestion. I guess from the observations, though, if you had H2O dissociating to H2, you'd probably make O2 as a product. And we looked for O2 and we didn't, maybe there's a hint of O2, it's unclear, but the O2 abundance is not stoichiometrically equivalent to H2. So I think that would be the issue for that kind of mechanism.
Why would you get O2? If they're from an individual water molecule dissociating somehow?
But so if you're starting with H2O and you're making H2, then the O has to go someplace, and O2 is probably the source where the O would end up.
Well, you start with liquid H2O.
What would be the alternative in the gas phase?
Well, OH and H or O, atomic oxygen. If you're photo or ionization dissociating the water.
Yeah, that'd be the primary product, but then, like, once you make those primary products, what would happen to the OH is the question.
Keeps going.
Goes to what?
Going up to the E-ring.
Oh, well, I mean, I think it would go up. I think it would probably react with other OHs to make O2 or hydrogen peroxide.
But the plume is collisionless.
How would you get the H2 then?
I don't know.
Yeah, it's an interesting question. So I guess the more general questions, like what kinds of solar promoted chemistry can happen in the time between stuff exiting from the tiger stripes at the surface to 50 kilometers altitude, and that has not been modeled.
Geysers on Earth are created because groundwater hooks up particular rock types and explodes, right? So I'm a geologist. We don't see this on Earth. We don't see ice on top of ocean creating geysers in any way. Like, is there a potential that these plumes are actually generated within that rocky core, and because the water has to accumulate under pressure and then violently explode? So why do you need an ocean? Is this framework like really well laid out so you know that there's a distinct boundary between rock material, ocean, and ice? Like, can it all coexist in some way, and you have pockets like kettles down there that can accumulate large amounts of pressure, heat, and then go off? Like,
I think it's possible you could have kettles like you described. In general terms, I think that three-layer structure seems like it's best supported by the data, because we have measurements from the Cassini mission of like the gravitational field of Enceladus, which shows that there's a concentration of mass further into the interior, which is a rocky core, and then you need less dense material, either liquid water or the ice shell above that. So you can't just have like rock very close to the surface, because otherwise it becomes, I don't know how you could understand the gravitational field of Enceladus if you had that. But I certainly think, like, as far as what the seafloor environment might look like, or how that water rock interaction looks like, that's not too clear right now.
I've got a question online actually from Brant. He said, in the really awesome mass spectrometry data for phosphorus, how can you ensure exactly which species correspond to the peak? And from the data, can you directly get the abundances / densities to compare against?
Yeah, so I showed the lab experiment where we did two things. So we first found those really weird masses, and they match phosphate species peaks. So then we decided to make those phosphate salt solutions, and we confirmed that they show up as we'd expect them to. And I didn't show any the last part of the analysis, which is then to look at other confounders for things that might alternatively have those peaks. And they're actually really weird species. I forget, like I think maybe some of them had chlorine or fluorine. They were like really weird things. So you have to, if they're not phosphate species, you have to try to assume really bizarre things. And the total evidence we have from what I just described, and then also the geochemical modeling we did a year prior, showing that, okay, when you have water in contact with the soda ocean, it's very plausible to expect phosphate. So when you kind of tie those pieces together, the phosphate identification makes the most sense.
Changing topic. Is anybody trying to turn the Webb Space Telescope at Europa to see?
Yeah, we looked at Europa also in late 2022. I don't have the spectrum shown here. Let's see if I can go back a little bit. So Europa, sorry about WebEx reminding me to do something. So in Europa, we don't see any of these fine scale fluorescence features. And in our paper, we reported that we did not detect any obvious signs of water vapor plumes. That was one signature. We also looked at the surface spectrum, and one notable difference on Europa is it actually had a decent sized dip here with CO2, which is different from Enceladus. So although they're both icy moons, they're different, right? Because one has an obvious massive plume structure. The other one either has no plumes or has very subtle episodic plumes. And then on their surfaces, one has a huge exposure of CO2 ice, and then the other body apparently lacks that altogether. So that's telling us something, that there's like multiple ways in which icy moons can evolve. So it's not like you have one icy moon, just like, you have Earth and Venus, right? From very simple bulk properties, they're almost the same, but yet their volatile evolutions have been dramatically different. So I'm not saying Enceladus versus Europa is like Earth and Venus, but it just shows that there's a diversity that we're still trying to understand.
Yeah.
Yeah, sure.
So why don't we see CO2 from Enceladus? If you're, well, basically, we consider the ocean is soda lake, right? Or soda ocean. Supposed to have a lot of carbon.
Yeah, well, one thing about Enceladus is we see CO2. So I left it out on the slides. We see CO2 gas in the plume. It's not a lot, but it's a little bit in the plume. That's from the mass spectrometry data that I skipped over earlier. But we think there's a soda ocean. So maybe like most of Enceladus's CO2 is locked into carbonates, and it has a soda high pH ocean. On Europa, maybe we see, a lot of CO2 because the pH is different, and maybe it's not a soda ocean in that case. And then if it's not a soda ocean, what does that tell us about what's going on with the water rock geochemistry?
One comment on sulfur. So if you consider from the equilibrium perspective, with that amount of hydrogen gas, it will be very difficult to have sulfate.
At equilibrium, that's why if you had abundant sulfate, it would serve as a source of energy because it would be in a state of disequilibrium. And there might be ways to actually produce sulfate because like I mentioned, the radiolysis process can happen in the interior. It's not particularly potent, but even a small process like that may over millions of years, it could still generate appreciable amounts of oxidants. So when we get back to Enceladus, 2040 or 2050, sulfate is something we want to keep a careful eye on.
All right, I think we'll leave it there. Why don't
Okay.
we thank Chris one more time.
Thanks for the questions.